Yeah. Good evening, ladies and gentlemen, and thank you again for your attendance to these wonderful talks, as we know. Tonight's speaker is Professor John Howe from SAMS, as some of us know it, which is the Scottish Association for Marine Science. Yes, it is. John is a geologist. He did his degree at Derby, goodness, followed by a PhD, he was saying, at Southampton, and yet it was actually situated in Edinburgh, I don't know why, but it was in deep water sediments of the North Atlantic. I know him from the turn of the century when he and three other young Turks, turned up at SAMS as new blood lecturers. And they're all still there, all four of them, of these guys. So obviously a good place to work. So that's the main theme for tonight is processes shaping the sea floor and post-glacial environments. Yeah. John, in his spare time, is a diver, big time, of the west coast there, and he spent 5 years with the Antarctic Survey, but I'm sure we'll give him a warmer reception than that. So I will pass you over.
So it is a privilege to come over to Perth and talk to you all. I do enjoy doing these things. It's great, and I wasn't expecting such a big crowd. It's really lovely to see everyone. So I appreciate it's reasonably close to Christmas, and it's a sort of a dark night. But thank you so much. So I wasn't. I was saying to Claire, I wasn't really sure how to sort of pitch this. So forgive me, and shout out any questions perhaps, or we'll leave them to the end, I think. But I wanted to talk about seabed mapping, and I wanted to talk about processes that shape the seafloor, but I'm going to talk in a very general sense about some interesting areas around Scotland and what seabed mapping can tell us about the processes, and in particular that Rob alluded to, that post-glacial history. But I'll touch on some other things as well, and we maybe mention about robotics and things. Well, as Rob has said, I'm based at SAMS in Oban, and I'm a marine geologist. Anyway, there we go. Which maybe I should make an apology for. It's my students remind me it's a kind of parascience. It's not. It is a science. It's an ology. I'm actually a deep water sedimentologist, so already I'm a fraud telling you about seabed mapping. I'm not a cartographer. I'm not a hydrographer, which is the term used for seabed mappers. People who really do map the seabed as a profession. But I'm very interested in the shape of the seafloor, features on the seafloor, and what that can tell us about our kind of glacial, perhaps, or post-glacial processes and habitats and heritage, our maritime heritage, and all these kinds of things. There are all sorts of mysteries on the seafloor, and you've seen it's coming around, our dinosaur egg. So that was trawled up from the North Sea. I think it's a septarian nodule. I think it's got a fossil in it. It's a concretion. It's not particularly mysterious, but there are all sorts of really interesting things down there. Now, there's a collage of silly photos. Geology is a remarkable science. It's been very good to me, I must confess, and it's taken us all over the world, not just mapping the seabed, but taking samples with an idea to try and reconstruct past environments. And you're probably arguing, typical geologists, they're always looking at the past. But the past is, of course, the best way to look to the future. We can study past processes, we can study past warming and cooling climates, we can look at changes in sea level, we can look at changes in the carbon cycle, and look forward to perhaps where our oceans might be going. So we've had projects all over the place in Africa I was talking to Rob about Indonesia, Papua New Guinea, all around Scotland, but particularly my forte is a little bit in the polar regions, is working in Svalbard, Greenland, and around Antarctica. Okay, so yeah, already I'm a bit of a fraud, but I want to tell you a little bit about the seafloor. So for this talk, I'm not going anywhere exotic. Sorry, because I have to say, and this is what I say to our students, there's actually a hell of a lot of mystery and some real interesting, fascinating, world-class, complex seafloor around our own seas. Some of the most exciting adventures I've had as a professional geologist have been literally looking out of the office window and the patch of sea in the Firth of Lorn. Extraordinary things, really interesting, and I'll show you some of these. So for this talk, I'm going to hopefully convince you a little bit about the case for seabed mapping, why we need to understand our seas, why we need to map our seas, above all. And then perhaps we'll have a look at the Sea of Hebrides, then we'll go to the Firth of Lorn and have a look at the whirlpool Gulf of Corryvreckan. And then look a little bit closer at the Falls of Lora in Loch Etive. So it's a bit of a west coast. I appreciate this is a very west coast view, more from the projects that we've had. And then maybe we'll have a look at some wrecks. And then finally, just a brief look at autonomy and robotics. I used to say this is the future. Of course, this is now. Robotic vehicles, underwater vehicles are now mapping the seafloor. They're being used to an extraordinary extent to map not just hazardous environments, but deep water environments. And I'll mention that a little bit as well. Before we get to the seafloor, let's just have a quick look. Rob mentioned SAMS. I'm always keen to tell people about SAMS. It's an extraordinary organisation. You could argue it's a little bit of a schizophrenic organisation. We never really know what we are, I think. We're an independent charity, which is quite helpful when you're working on projects. We are completely independent. We're a partner of the University of the Highlands and Islands. We're based in Oban, but I'm very proud of our heritage. And you can see the panel up there in the top right. SAMS grew from the Challenger expedition, which left Woolwich Docks in 1872 with Wyville Thompson and Sir John Murray, and spent 4 years sailing around the world collecting the first oceanographic data. They were the first people to measure the depth of the Atlantic. They were the first people to study and sample deep sea sediments. They were the first people to discover the mid-Atlantic ridge. And SAMS grew out of the Challenger expedition. Indeed, the volumes, the description of the Challenger expedition are now held at SAMS in Oban. But there's a good view of the site, and you can see in the background there's Loch Etive, and just faintly you can see the Connell Bridge, and we'll come to that in a moment. But we're in a really lovely, possibly unique site to study marine science. We're in an area that is fed by pristine Atlantic waters to some extent, but also we have the estuarine fjordic conditions of the sea lochs all around us. And locally, very deep water. We have over 200 metres deep water basins within about half an hour or so sail from the laboratory. So we're a great place to teach students, but we're a great place as well for studying science. And the flavour of SAMS' science is international. We're all over the world, looking at from the deep sea to shallow water coastal environments in the tropics, seaweed, aquaculture, deep sea mining, all sorts of different aspects, some controversial aspects that maybe we'll touch on in a moment. So it's a really terrific place. I was saying to Rob over a bargee just now, but at the end of the day, if there's one thing I'm very proud of, and it's the reason that I came up to Oban, is our undergraduate programme. And people, rightly so, are quite surprised that we have over 100 undergraduates studying marine science with us at SAMS. And we now offer a variety of different pathways to study, not just pure marine science, but you can study Arctic environments up in Svalbard, and you can spend up to a year in Svalbard at the University of the Arctic in Longyearbyen. We also have specialisms for students in robotics and oceanography, and our new one, which has just taken off, actually, it's remarkable, in marine biology. We've been doing expeditions. There's a recent diving expedition to the Red Sea in Egypt, and we have all sorts of opportunities and exchanges with Canada and with universities in the US as well. So it's been a terrific experiment from our past director, Chris will remember, Graham Schneeld, and it's really taken off. It's a terrific course. So spread the word, really, is the message, if you can. Okay, so, now is a good time to be doing marine science, to be interested in the seafloor and interested in the processes of our oceans. But these are challenging times, without doubt. These are extraordinary times. Our oceans are changing at an unprecedented rate. There are all sorts of challenges, not just things that we hear about in the news, such as ocean heat waves and climate change, global warming, but all sorts of things that we should be worried about, we should be interested in. This is just a quick skim through. This is me looking through BBC News and New Scientist, selection of stories since October. And you can see here, this is one I picked out just a couple of days ago. Deep sea mining tests prove the impact on the animals living on the seafloor. Not surprising, really. But some other interesting things, other people, other nations are interested in our seabed. Coral reefs are struggling. Coral reefs, the Sclerectinia, the order of corals, are at a tipping point, surging global temperatures. We're seeing through the summer around the UK an ocean heat wave with elevated temperatures in many places around the UK. Antarctica, as I say, one of my favourite places, may have crossed a tipping point with coral reefs, tipping point with Antarctica. A tipping point is a change in state. The oceans are approaching a tipping point where they're becoming, moving to a different state of function through global warming, through the introduction of pollutants, microplastics, invasive species, and global industrialization and exploitation. So we need to find a way forward. These are difficult, huge challenges, wicked challenges they get called sometimes. And we need to find a way to use our seas more sustainably. But to do that, we have to try and understand them. They're still relatively poorly understood, surprisingly. Even though, Wyville Thompson and Sir John Murray went on their expedition, a very long time ago, 120 odd years ago, we still have so many gaps in our knowledge about the seafloor. So let's make a case then for mapping the oceans. The oceans are, surprisingly, relatively poorly mapped. And I always say to people, perhaps unsurprisingly, the geology of our continental areas, the geology of the UK or of Greenland, extends out beneath the oceans, but it's a very difficult place to work. It's a very difficult place to really understand some of those geological processes and to be able to map and therefore be able to predict the rocks that are there and perhaps decipher any environmental records. We simply don't know enough about what lies beneath the waves. A good case in point is this interesting, perhaps controversial idea of Zealandia. This is a continent, a new continent. So we know the continents, don't we? But here's somebody's come up in 1995 suggesting that New Zealand lies on this extended bit of seabed, and that this bit of seabed is actually part of New Zealand. It's a continental area as opposed to an oceanic area. So our Earth is divided up into layers. The outermost layer is that rigid layer of the crust, the lithosphere. And we know there are two different sorts of lithosphere. There's young, thin, hot oceanic crust, which is quite dense. And then there's lighter, perhaps older, continental crust as well. So the suggestion is here, we mapped the sea floor, these workers mapped the sea floor and discovered a new area of continental crust, and they've named it Zealandia. That's quite a surprise, isn't it? You think, how on earth did we miss a continent? God, slip down the back of the sofa, that one. But we don't map the sea floor. We haven't really got a good idea of what's down there, which is quite amazing. So how do we map the sea floor? So we use sound, sonar, typically, to map the sea floor. Sound, navigation and ranging, sonar. So this is where we can put pulses of sound or blocks of sound out onto the sea floor and analyse the pulses of sound coming back. And we can either measure the time it takes for the sound to hit the sea floor, or we can look at the quality or the intensity of the sound that's reflected back. And that gives us a clue as to the composition of the sea floor, if we're looking at the intensity, or maybe the shape of the sea floor, if we're measuring the time it's taken. But we can do other things as well. We might want to look below the sea floor, and we can do that with sub-bottom profiling, putting energy into the water column. Can be difficult for some animals, for cetaceans, for mammals. That's quite a difficult thing to do. It's quite affecting of animals and seals and things like that. Seismic reflection profiling. But you might be able to look at that reflected sound and see the layers below the seafloor and interpret the character of the seafloor below and look at then past climates or past processes. You might be able to look at side scan sonar, a bit like sort of shining a torch at an object and getting a shadow and a reflection back from the seafloor and getting an image in sound. And that's a great way to look for things on the seafloor. If you lose anything, let me know, because we'll look with side scan sonar on the seafloor and you might be able to find things, shipwrecks, bicycles, maybe not wedding rings, but it's a really good system. It's my favourite, I have to say. I'm going to focus, you can see there, I've put a little circle on that, an ellipse, on bathymetric sonar. So this is multibeam echo sounder. This is multiple pings of sound that will image the shape of the seafloor and provide us with a three-dimensional view. In some cases, depending on the depth of the water, in shallow water, say to centimetre scale. It's a really terrific way to do this. But these are all great, aren't they? You know, I mean, we can get a good idea of the character, the composition, objects on the seafloor, but you still have to get in there. You still have to get down there and you have to sample it to prove what you're interpreting. So there'll always be a place, I'll always say, I'm not quite redundant yet. There'll always be a place for a geologist, because at the end of the day, this is all remote sensing. You've still got to get down there and get some samples. Okay, where are we then with mapping our oceans? And surprisingly, we're not doing very well. Okay, so there was a tragic event in 2014, March 2014, when Malaysian Airlines MH370 was lost. And it's assumed, the aircraft with hundreds of people on board is assumed to be somewhere off Western Australia in the Southern Ocean. This is an area that wasn't previously well mapped. So all the search effort has been mapping an area where there wasn't actually good maps to begin with. And people realised, not just geologists, but politicians realised that we really needed to have better maps of the sea floor. So the Nippon Foundation, combined with GEBCO, the Committee for the Bathymetric Atlas of the world, the Global Bathymetric Atlas, joined forces and they funded the Seabed 2030 project. This is terrific. If you want to waste an afternoon, this is absolutely brilliant. Go on their website and they've got a globe and you can choose what bathymetry data set of the sea floor you want and you can fly around. and have a look for things. Look for Atlantis or the Millennium Falcon even. People seem to enjoy that kind of thing. But at the end of the day, JEBCO, Nippon Foundation, Seabed 2030, we're not that far away, are we? They've only mapped 27% of the ocean floor. We're a long way short. We're a long way short of mapping our oceans. The good news, perhaps, hopefully, fingers crossed, for MH370, is that the Malaysian government has signed a deal with the big Texan robotic firm Ocean Infinity, and they're going to go back at the end of this month and resume the search again, and hopefully, God willing, they'll find those people and they'll find that wreckage. But it was the loss of MH370 that really kick-started a kind of global initiative to really start to map our oceans. If you're looking for something, you need to find the difference of that thing on the seafloor. If you don't know what the shape of the seafloor is to begin with, you haven't got a hope to find something on the seafloor. Very difficult job. Okay, so closer to home. Multibeam, really good quality maps of our seafloor around the UK account for about 27%. I read a thing recently, that's the UK Hydrographic Office statement in 2025. I think it's actually more like 40%. It depends on the quality of the mapping that's going on. There's some really good maps. I'll show you in a bit. In 2014, we mapped Loch Etive. Chris will remember Loch Etive. And I'll show you in a bit. It was done with a bloke with a piece of string, or a woman, with a piece of string. And they measured the depth, and they measured it by dropping a wire weight. And we went and mapped it for hundreds of thousands of pounds. And we found their map was actually as good as our map. So there's still some, there's still some really good stuff with very cheap things. Only 10% of coastal states have over half their waters surveyed to a modern standard. By modern standard, we're talking about the International Hydrographic Organization, the IHO. 80% of the UK is under the sea. Us Over 70% of the Earth is ocean, and we haven't really mapped enough. Here's two examples just to get us in the kind of mindset of looking at multibeam. This is multibeam sonar. This is data. This is actual data. The top left-hand panel shows anchor drag marks. Do you see the seabed has got like lines and blobs and weird shape to it, tessellated shape? They're anchor marks. So that gives us an idea of the kind of the power of this instrument, that we're able to image the seafloor enough to see where ships' anchors and anchor chains have dragged on the seafloor. We can also look at trawling. I'll show you some examples a bit later on of trawl marks. The lower panel, again, is off Oban, just to the south of the Isle of Kerrera, between Mull and Oban. And these are holes in the seafloor, depressions, and this is where gas has escaped. And this gas could be methane. Methane, is a greenhouse gas. And these pockmarks represent where naturally gas has seeped out and the gas-charged sediment beneath has kind of sunk back. So it's not kind of a dramatic volcano. These things would seep. The pockmarks, they're very common. We found thousands around the west coast of Scotland, and they're originating from that huge organic load. If you've seen the weather for Oban tomorrow, oh dear. And all that rainfall is going to wash all that organic, peaty, vegetable material into the sea. It'll settle out, be buried, and then will be digested and microbially within the sediment, and those gases will be held trapped within the sediment, and eventually they could be released. They could be released dramatically or slowly and produce these pockmarks. Really interesting. Multibeam sonar. It's fabulous stuff. I'm obsessed with it. Now then, maps. Love maps. This is an Admiralty chart area that perhaps many of you are familiar with. This is the Sea of Hebrides, and this chart has been compiled from multibeam sonar. So we're here off the Ardnamurchan Peninsula there, and we've got the Isles of Muck and Egg and Rum there. There we are, Muck, Egg and Rum. Now the data that's been used to compile that is multibeam sonar. So there, if we overlay the multibeam on the chart, there's the data. You know, it's remarkable. So hot colours, the reds and the yellows, are shallow water. Oh, sorry, I should have said this earlier. Are shallow water. This is about 50 metres or so, or shallower. The colder colours, the greens and the blues, are deeper water. So that would be over 100 metres. The blue there is about 200 metres deep. So already we're sort of getting a feel for the shape of the seafloor and the kind of detail we can see on the seafloor. Now, the most obvious thing you'll have noticed here is this absolutely terrific fault running through. This is the Fascadale fault that's come through from the Ardnamurchan Peninsula and runs all the way up towards Rum. There's some other really interesting features. I'll show you another photograph of this a bit later on. We can see softer sediments, we can see gas pockmarks there, just about visible. And I'm indebted to the British Geological Survey for sort of preparing a lot of these slides this evening, because this is multibeam sonar data, seabed data, draped with radar altimetry. This is radar data of the island. So the black islands, the landmass, contrasts nicely with the multibeam data. Okay, here's a bigger view. That's what we were just looking at to the top, the white hand panel. This is all probably a bit old now. This needs updating. This is multibeam coverage for the west coast of Scotland. Absolutely fascinating. Absolutely love it. It's incredible. So we've got Skye to the top, we've got Mull in the middle there, and then we have the Firth of Lorn here, and Isla and Colonsay and the rest of it. Really interesting, because what strikes me is we've got these deep basins. Hot colours are shallow, cold colours are deep. And you can very vividly see these basins in the Firth of Lorn and basins in the Sea of Hebrides, and they tell us something, they tell us a story. So I'd like to show you some examples of bathymetry from the Sea of Hebrides, and then we'll follow that up with the Firth of Lorn. So to start with, brilliant. This is 2,200 square kilometres of multibeam data from the Sea of Hebrides, and this was collected in 2011. So this is quite old data now. And this was part of a programme known as the Civil Hydrographic Programme, CHP, and it's led by the Maritime and Coast Guard Agency, the MCA, under the auspices of the UK Hydrographic Office, which is a terrific programme. And what they do is they give out contracts known as hydrographic instructions, and people can bid in if you're a commercial organisation, or if you're a university and you have the equipment and the know-how, you might be able to bid into some of these contracts, and you can map the seafloor and use the data and all the rest of it. It's a great programme. And here we can see an enormous diversity of features, not just our pre-glacial, pre-quaternary geology, so older than 2 million years, and this includes these lovely platforms. These are volcanic rock. Here we've got our basalt platforms. We also have these older billion-year-old platforms of Torridonian sandstone, but we also have outcrops of Mesozoic, Jurassic and Permian rocks as well. But you can see the area is dominated by these amazing faults. The Skerryvore fault running up the side of Colin Tyree, the one we've just been looking at, the Fascadale fault, and the Camasunary fault running along the side of Rum. It's an incredibly diverse landscape. Geologically, solid geology, the rocks make up some really interesting things, but also our glacial and post-glacial history for this area can be deciphered from the shape of the sea floor. So a really, really terrific area. So I'm going to have a quick look around the Sea of Hebrides. So our first area is around on that Canna High. So we're up there, look, with the little, where the arrow is pointing. And it's a really odd seabed, I think. So this is basaltic rock, as I mentioned, so it's maybe 50 to 60 million year old volcanic material. But in this case, we can see these grooves, these rather large grooves from 100 meters to 1 kilometres long. A seabed relief of 1 to 5 metres in water depths of less than 70 metres. So this is produced by subglacial. This is overridden by ice. This is fast flowing ice. Presumably, after the last glacial maximum, which was around about 27 to 30,000 years ago in this location. So this shows where ice is whizzing along. Could be as fast as 350 metres a year. It's flying along. It's an ice stream. And we can see ice streams around Greenland and around Antarctica today. And we're very interested in the behaviour of ice streams because they're the taps that are holding the ice sheet back. If ice streams start to rapidly move and fail, then there's nothing really to hold on to the larger ice sheet behind. So this is interesting. This shows us we have rapidly moving ice in this location. And there's been various reconstructions to look at the retreat of the ice and the decay and loss of the British-Irish ice sheet. And that's interesting for us, for our history, and for our landscape. But it's also interesting to think about the future of Greenland and Antarctica. We're just off between the top of Rum here and the Isle of Southern Skye there. And here we see these wonderful rock basins. Hot colours are shallow, cold colours are deep. And in this case, we see these up to 5 kilometre wide, 5 kilometre long, deep rock basins. The theory is these have been quarried out by extremely high pressure water below an ice sheet. Vast amounts of meltwater are literally funneling through and are quarrying out these softer rocks underneath. Northeast of Rum, glacial ice was flowing through a trough south of Skye and collided with this more resistant Torridonian rocks, and it was stuck, causing localised erosion and quarrying out these deep troughs. If we want evidence of the impact of ice, then we look to the west of Rum. It's a bit difficult to see, but I think these are terrific. Look at these lovely little feathery, they're actually quite big actually, moraines. These are moraines. I showed you evidence of fast flowing, streaming ice, but here we have lovely superimposed ridges on the sea floor and numerous little moraines. This shows us where ice isn't flowing fast, but has pushed out, stopped, and is now retreating back. So we're getting a really interesting glacial history from these areas, from this seabed bathymetry. Now then, the Muck Deep. I don't know if it's called the Muck Deep, but we call it the Muck Deep. Muck's over here. Muck's just sort of up to the top of the slide. The deepest point, I've got to tell you this, the deepest point in the UK is the inner sound of Raasay, and it's 321 metres deep. The Muck Deep, we went up and down, trying to get deeper than 321 metres, and we couldn't. So it's official, the Muck Deep is the second deepest hole around the UK, which really annoys me. The inner sound of Raasay is a fascinating area. It's the British underwater testing facility, and many of you probably know up at Kyle, the MOD and the Royal Navy run their submarine testing range. It's a really lovely place, it's really interesting. But it wins for being the deepest. Muck Deep, I hope you'll agree, is a fjord. It's a drowned fjord. Look, it's a glacially over-deepened basin that's then subsequently infilled with sediment after the ice has retreated. But it's the second deepest hole in the UK, which keeps me awake at night. And then finally, maybe we can go back to some of those interesting features. Here we have our fault, the Fascadale fault, but also interestingly this buried rock basin to the east of Egg. This is showing where the sediments have come down, the sound of sleet, and infilled that rock basin. But there are some really interesting features on here as well. We have these volcanic features, radial dikes coming out from Ardnamurchan, and this wonderful thing. Do you see this wriggly worm on the seabed? Absolutely amazing. So there was all sorts of speculation as to what this was. And I was lucky enough in 2011, we went back with the James Cook and a drill rig, and we drilled that with the British Geological Survey. And it turns out to be a lava flow that was in a valley. And the valleys have disappeared and been eroded, and we're left with this little wiggly, resistant lava flow. So it's an old landscape. It's an exhumed landscape that's been eroded. It's absolutely fascinating, incredible. So we're seeing quite an interesting picture. And we're seeing evidence of our glacial past. So we can start to make some reconstruction. This is a crude reconstruction from a study that we did years ago. This is showing ice at last glacial maximum, LGM, last glacial maximum. So the maximum extent of ice out on the shelf, reaching the shelf break about 27,000 years ago. But we can see components, elements of that ice that were faster flowing. And in this case, we can speculate from the Sea of Hebrides, we have the Hebridean ice stream, the Barafan ice stream, and then really interesting to the north, the Minch ice stream. These ice streams are faster flowing, they're collecting sediment and they're depositing them in deep water to the north and south of the Outer Hebrides. So it was the Outer Hebrides that effectively produced a barrier to ice flow. So the ice cap, as the ice flowed, it flowed north and south of those more resistant rocks, and they were an effective barrier. And then the ice retreated back. Now today, there's a lot of interest in the Minch ice stream because the collapse and retreat of the Minch ice stream is telling us an awful lot about how the West Antarctic ice sheet might collapse. And there's a lot of studies going on. The most recent being Neil at the University of Stirling, and Tom Bradwell and many others have been looking at this. So really interesting area, fascinating area. Okay, I'm going to jump about and we're going to move south now. Apologies for jumping about. So we looked at the Sea of Hebrides and we looked at our glacial history. Let's have another look at an area with a very diverse history of both glacial and solid geology. This is the Firth of Lorn, this is Oban, Kerra, Mull, and this is the bathymetry of this area. It's a much smaller area. Already you can see we have 2,200 square kilometres. This is 553 square kilometres with a maximum depth of 261 metres. This was also a survey that was conducted and led by the Maritime and Coast Guard Agency and was part of an EU, remember them, funded project known as Innis Hydro. This is the Ireland, Northern Ireland and Scottish hydrographic survey with a collection of universities and institutes from around and across the Irish Sea, all working together to produce these wonderful maps. Now then, geology. If we look at the British Geological Survey map, here we can see the coastline in white, and you can see a lot of detail onshore, understandably, but offshore, we're not really getting very much detail. We're missing that. The stratigraphy of the rocks, the age of the rocks, and what they tell us go from the Precambrian, older than 550, 570 million years, and then all the way through to fairly recent, less than 60 million years or 2 million years or so, tertiary. We have two big erosion surfaces in here within the Firth of Lorn, separating the Precambrian Dalradian, the Eastdale slates and other rocks from the Old Red Sandstone, the Silurian Devonian. And then between the Old Red Sandstone and the New Red Sandstone, the Permian, which is, sorry about the slide there, it's about 200, 250 million years or so. So it's quite an interesting geology. Now, if we zoom in, look at that. This is pretty much the same area that map showed. And I've ignored the onshore. And look at that. What an amazing structure. This is a fault-bounded basin. That diamond is a fault-bounded basin and shows the effects of this area has been intensively faulted. It's an area that is an offshoot of the Great Glen Fault all the way up to Inverness. And it shows how there's been extension of the crust in this area. And these lines show where the seabed has dropped down and subsequently been excavated out by ice and by erosion over many millions of years. So we have a lovely complex history of softer, older sediments surrounded by younger but much more resistant volcanic rocks and some sedimentary rocks as well. Really amazing, and we didn't expect that. We didn't expect to find a gigantic diamond on the seafloor. If we take a slice through that, this is between Mull and the Sound of Kerrera. Here we can see, and I'm indebted to Roger Anderton, local geologist around Oban. I'm indebted to Roger for deciphering this. Here we see our softer, older Dalradian Precambrian sediments with a little bit on Mull of more Mesozoic and Paleozoic sediments, deformed, and then this lovely unconformity here, and the old red sandstone and the volcanics lying across this faulted basement of the Easdale slates. And that gives us the shape of the seafloor in the Firth of Lorn. So if we keep that in mind, and then go back to our ocean floor map, hot colours are shallow, cold colours are deep, in this case about 200 metres deep as a blue. And here we see this beautiful bathymetry, the shape of the seafloor. Look at these lovely arrowheads, arrows. And this is folded rock that's diving down below the seafloor. These are folds, tight, old folds. But we can also see these resistant blocks of volcanic material and the more recent history with our glacial moraines. And then in this area, look at this. This is great fun. The seabed's fallen away. We've got a submarine slide. It's a collapse feature. These are unexpectedly common. Maybe they should be expectedly common, but this is a collapse feature. There's some great ones up the Sound of Mull and around Little Loch Broom and other areas as well. So these are collapse features. So we're going all the way through from the Precambrian, 550 million years, all the way through to, we don't know, relatively recently, perhaps a few thousand years. Now then, if we take just a brief snapshot across the Firth of Lorn, and again, we get a lovely sort of view across here, across from the Isle of Easdale, across to Mull, north of the Garvalands. And we can see these rock platforms of old red sandstone and Lorn lavas, exposed rock surfaces, the Easdale slate, and that lovely arrowhead morphology there again, showing these plunging folds. Now there's a story that I didn't believe. Apparently, Fingal's Cave, Staffa, the Giant's Causeway, apparently they're made by giants. And these giants, there was Finn McCool, the Irish giant, and Brennan Donna, and they fought, and I'm not sure of the story, but they fell out. I think Finn McCool disguised himself as a giant baby and frightened Brennan Donna, and he ran back across the Irish Sea, ran back across to Scotland, and hid because he was so big. Finn McCool was so big. And they threw stones at each other. Well, I didn't believe it. And then, on the ocean floor, oops. There's a giant's footprint, which clearly shows that Brennan Donna was running away. I said there'd be mysteries. Lots of mysteries. Let's go to the Witch's Cauldron. The Whirlpool Gulf of Corryvreckan is the fourth largest whirlpool in the world. Top is the Solstrømmen in Norway and alongside Naruto Narrows in Japan near Osaka Bay. This is our very own whirlpool. This is the Corryvreckan. Now, incredibly, we mapped the Corryvreckan. We had fun and games. We really did. What an interesting place. What a magical place. We ran aground, actually. We bumped on the rocks, which is not a great thing to do. The functioning, how does the Corryvreckan work? What makes the whirlpool? Well, you'll see on YouTube, or you'll see reconstructions showing these pinnacles and lumps, and they're broadly right. They are broadly right. But what we've been doing is investigating the Corryvreckan and hoping to decipher the mystery of the Corryvreckan. Now, this is an animation, this is a numerical model showing the behaviour of the tides between the flood tide and the ebb tide flowing through the Whirlpool Gulf between the islands of Jura and Scarborough. It's rather hypnotic, it's kind of like lava lamps. And I'm indebted to Andy Dale, who had a project funded called The Great Race, which was examining this. So this is Andy's model. And you'll notice as this jet of water on the flood produces these vortices that spin out from the Corryvreckan whirlpool, from the Gulf, sorry. And you look at these lovely vortices coming out. Now, if we look at what's producing that vorticity and those jets of water, we can again look to the seafloor. This is the Whirlpool Gulf of Corryvreckan with no water. This is it stripped away. This is real data of the Whirlpool Gulf. There's the whirlpool, and there's no pinnacle. It's a rock. It's a little rock bump that sticks out. Presumably, this is a rock dike, an intrusive, cooled, igneous, made by fire, cooled from a molten state. It's a resistant rock sticking out. But interestingly, we've got water depths of about 220 or so metres here. But as you go out across the Great Race, we can see the effect on the seabed of these really vigorous flows of up to 4 metres per second, 8 knots or stronger in some places. If we look from the Great Race east, you can see there's that little rock wall. So that's what's producing, in some cases, the whirlpool. There's the rock wall there sticking out. And the whirlpools are generated on the downside of that rock wall sticking out. But we've got this dune field here and dunes here, and they coincide with that numerical model showing where the vorticity is produced on the seafloor. If we look up the Great Race, this is from the east looking west. There's a nice view of the rock wall. Now, the interesting thing is, with Corryvreckan, is we've been doing some follow-up work, and again with Andy Dale, Neil Burnside, Al O'Dell, and Rich Dale have been doing aerial surveys using an aerial vehicle and taking time-lapse photography. And the whirlpool moves about. The whirlpool starts on that rock wall and then moves down the Corryvreckan, dissipates, and as it dissipates, another whirlpool forms, and you get chains of whirlpools that we hadn't realised. And this is a really interesting fluid dynamical problem to try and understand how these chains of whirlpools form, produced by that jet of water sloshing backwards and forwards within the Gulf of Corryvreckan. Okay, well, I've coming to a conclusion now, but I'll just finish off by just looking very briefly at the Falls of Lora in Loch Etive, which is, we've looked at the Corryvreckan, which is an extremely energetic area. The Falls of Lora are also an extremely energetic area, and it's driven by changes in tidal height over a very shallow rock sill. And I know many of you are very familiar with this area. I'm diving here on Sunday, which I'm really looking forward to, because we're going to have a lot of rainfall, and it makes it quite interesting to be under the bridge when there's been a lot of rainfall coming through. And I'll show you some pictures. So the tide outside of the Connell Bridge at spring tide has a 4 metre range. If you just go inside Loch Etive, it has a less than 2 metre range. So the tide inside Loch Etive is doing this, and the tide outside is doing this. So there's water, a lot of water trying to get out, and there's a lot of water trying to get in over a very constricted area. And it's a really fascinating place. We love it. And it's a great place for kayaking, for diving, and for all sorts of silly things as well. It's a really good place. And occasionally we get the big timber boats coming up, and occasionally they hit the bridge and the bridge gets closed. You'll be aware of this. So in 2014, again, apologies, it's quite old, we mapped all of Loch Etive, and as I said, it agreed with the old boys who measured it with a wire line. You know, it was a really good survey they did in the 1930s. I think it was 1936 was its last survey. So we mapped it with sonar, and it produced some really nice results. Fascinating area. I'm not going to talk too much about the inner basin, which in itself is really fascinating from a biogeochemical point of view, because it gets deoxygenated, it gets hypoxic, very low or non-existent oxygen, and then during a dry spell, water manages to get in because the loss of fresh water, if there's a lower freshwater lid, then the marine water can get in and overturn and oxygenate the basin. And that's got implications for the biogeochemistry of the water, but also the animals that live there. But I'm going to show you the Falls of Lora just very, very briefly. And there's the bridge, there's the rock sill, and we have some beautiful seabed. So this is where our usual sort of dive sites are, within these holes, and if we're feeling brave and there's a good tide, then we explore this cliff to the west of the bridge. But you can see we've got areas of mobile seabed. This is seabed that is being moved around by those vigorous tides. These are gravel dunes. They're dunes of pebble cobbles. Really, really interesting. If we look to the east of the bridge, and this is from Christian Armstrong's work that he published a couple of years ago, these are these gravel waves. Now, what Christian found out is that during periods of intense fresh water, could be natural through heavy rainfall, or even through the dam release at the River Orr barrage. If they release water, these gravel waves actively do migrate, so that the seabed will change during intense spells of freshwater release. But I'm really interested in the sharks, which are amazing. Critically endangered population of spurdog live in Loch Etive and perhaps some other lochs. Didn't really know. You know, they are wonderful, wonderful animals. But they survive these hypoxic events. They move out, but they stay within Loch Etive. They should go out into the deep water areas of the North Atlantic, but they typically stay. They've been tagged, and researchers from the University of St Andrews and now Napier University are studying this really unique population. And they're wonderful animals, and you can dive and see these creatures in their natural habitat. A quick model. Oh my word, what's going on under the Falls of Lora? Well, you can see here a block model of the bathymetry, taking our bathymetry and then trying to decipher the effects there. And we can see here the ebb, the really strong ebb flow flowing out, and that's driven principally by the introduction of fresh water, and that will change these gravel banks to the east of the bridge. Now, I can't finish a talk on the seafloor without showing you some shipwrecks. And I'm sure many of you are familiar with the Breda. The Breda's probably one of the most famous wrecks in the UK. So it was sunk in 1940. There are all sorts of great rumours and things about the Breda. So this is our sonar. This was done from an autonomous underwater vehicle. This was a survey from a robot. It's terrific. I first dived the Breda in 1992, I think it was, and the ladders were all straight ladders. If you go back and dive the Breda now, you'll notice the ladders are C-shaped, which gives me the willies. So the Breda is actually all collapsing down, and we can monitor that. We can see changes from the bathymetry. You can see the wreck actually settling now. Probably not helped by lots of divers and lots of bubbles, and just naturally collapsing down. But the most exciting thing, as I said, that I found was undoubtedly aircraft. And off the coast of Oban, there are at least 7 RAF Coastal Command bombers on the seafloor, which was extraordinary. So from our surveys, we found little bumps, just little bumps. We didn't really know what they were. And then with a local diving club and working with Wessex Archaeology, we went out and dived them, and there are these wonderful, now protected wreck sites of Short Sunderland, Sarrow Lerwick, bombers, and there's probably others to be found because the Connell airfield in Oban was an RAF Coastal Command base. There's some photographs. This is from a Sarrow Lerwick bomber off Lismore. This is the throttle from a Sunderland, inside the cockpit of a Sunderland. There's a Sunderland. This is side scan sonar, and there's the wreck. There's the wing and the tail here of a Sunderland, and this is a trawl mark that's just missed this war grave. Now then, to end with, as I said at the beginning, a few years ago I would say, well, let's look to the future. This is now. This is amazing. It's absolutely amazing. And the technology is getting really advanced now, to the extent that the Tonga volcanic eruption in 2023, it was January 2023, was mapped by a robotic vehicle, no people, from a desk in Essex. It's amazing, isn't it? There was nobody there. This thing was deployed, and then they all went home, and these guys sat in Essex and mapped a volcano in thousands of metres of water that's 16,000 kilometres away. It's extraordinary. So at SAMS, we operate Freya. This is Freya. So Freya was part of a team. We were in Greenland last summer, and we were using Freya to map the seafloor in front of marine terminating glaciers. And as I said, this is a really important area of study, because if we understand the shape of the seafloor, then we understand the processes that are affecting the ice, and we might be able to understand then where we're going in the future with the retreat of ice and the change that we're going to see in the next few thousand years to our planet. Freya's rated to 500 metres water depth, and we can put all sorts of sensors on. She runs for 8 hours and is completely autonomous and is owned by the UK government, and we operate her on behalf of the UK government. And on that note, I'll say thank you very much. Sorry, it's run a little bit over. Thank you. I'll end there.
Enthralling. Any questions for John? Well, I think we're all yes.
With the expansion of the sort of renewable energy, putting in more and more cables into more of these places, is that increasing the amount of surveying that's happening with the increase in telecoms and
Yes.
cables and everything else?
Yes.
Is that kicking back more data, or is it generally in areas that were mapped previously?
A bit of both. Depends where you go. It's a bit peculiar in the UK because, unlike many other nations, we don't have a national seabed mapping campaign. You can see my hobby horse. Norway, Ireland have completely mapped their continental shelf, and there it is. It's free for everyone. UK government are funding the civil hydrography programme, where they'll allocate to certain priority areas. But an operator who's building a wind farm will go and do their own survey, and they'll hang on to it because they paid for it. So it depends on where you go. Yeah. But what we want is everyone just to share it. But of course people won't. But we get there. We will get there.
So the mapping around Vera and Lorn, Cana, can you actually, the public look at
Yes, it's all, I should have said, sorry, all that is publicly available. If you go to the UK Hydrographic Office website, there's a thing called Inspire, and it's not the best website. Is this still being recorded? Great. It's a terrific website, and you'd be able to navigate it really easily. And you'll look for an area that's called the Data Archive Centre. There's a little map viewer, and you can view all that data. And if you want to, and if you've got great broadband, be warned, you can download it all yourself and fiddle around with it. Yes, it's all publicly available. Everything I've shown is all publicly available.
Any other questions? Yes?
So, how deep does your boat-based sonar actually go? And at some point, could you use satellite or do submarines?
Yes, so thanks Claire, that's a good question. So vessel-based sonar, as you can imagine, is on a triangle. So the deeper you go, the bigger that triangle base is. So the lower your resolution is. So you can have full ocean depth multibeam, but you'll image the size of Perth. You know, it's not going to, you'll see lumps and bumps. Can you do it by satellite? Yes, you can. But again, it'll be kilometre scale. You can measure changes in ocean height by satellites that are mimicking the sea floor in thousands of metres of water. It's not that resolution. It's just a general view of the shapes of the lumps and bumps, kilometre scale. If you want high resolution bathymetric data, you've got to shrink that triangle down and get that footprint of sound smaller and smaller, and you can get higher and higher resolution. So it depends on what you want. But robots are definitely the way to go. So this May, how about this? This is going to go horribly wrong. Oh, I'm still being recorded. Great. It's going to go really well this May. So we're working with the British Antarctic Survey and the University of Cardiff, and we're going to put in a swarm of robots, and we're going to test them off Oban. A swarm. It's going to be about 8. And we're going to try and map the sea floor, and they're going to talk to one another, I hope. And they're going to swim around and talk to one another and be a coordinated thing. The idea is, we know what the seabed around Oban's like. They're going to be used off Antarctica, and they're going to be dumped into the Southern Ocean, and they're going to go off and map the Southern Ocean. Fingers crossed. And that's the way things are going. Swarms of robotic vehicles.
So how do their batteries last? Because if you buy a drone from Argos, it runs out almost before you get it going, and they can't be that big.
No. So that's
the water is cold. So
that's because you bought it from Argos. So with the greatest respect. But yeah, no, you're absolutely right. A good underwater mapping vehicle would probably last about 24 hours. Is about the best you'll get. So they'll need to come up, and they'll need to be recharged, swapped over, and sent back down again. So again, you're still going to need people. The difference is with that robotic boat that I showed you, where they can last, they can have solar and to some extent diesel generators, some of them, and they can last for months and months and months. So those ocean-going autonomous vehicles are really good and will last a long time if they don't get knocked over, smashed to bits, or lost, or hit by a boat, which we've had. But you still have that same problem as you're on the surface. You need to get down deeper. So if you dive deeper, you can map small areas in very high resolution. If you stay on the top, you can map massive areas in low resolution.
Tom.
Yeah, so presumably your submarine things know where they are because they're getting a GPS signal.
Yes, but not underwater.
Oh, that was
So-
my question.
Yeah,
How
so
do they know where they are when they're underwater?
because we send in a little pinger, we put a little pinger down and we talk to it, and it relates itself to where you are. So we're constantly talking
Right.
to these things underwater. They'll get a GPS fix on the surface. Some places, like Loch Etive, is notorious, big mountains, they don't really, has a terrible GPS coverage. But they would get a fix, then dive down, and then we would talk to them. And also if they get stuck, which happened a few years ago, we'll be able to think, hang on, you're in the same place for the past 4 hours. And we might be able to get some information about what's happened. It's stuck in a fishing net or something. And then you have to make the call to go and get rescued. Sorry, I'm rambling.
Just to clear, all the communications of these, is it all by sound? Because you can't.
Yeah, by sound. Yes, by sound. Yeah.
I've got a question about the dredging. You showed that Clinton could see the marks.
Yes, the trawl
marks.
mark. Yeah.
So could be a threat to some fishing. In the fishing community probably don't want to know about dredging. I come from a fishing background myself, but with other boats coming in from the EU and stuff, and there's a lot of damage being done by dredging. Is anybody taken on board that this is a real problem for marine life?
Lots of people, Scottish Government, there was a consultation, there's going to be a new consultation, I believe, I don't know, thank God I don't get involved too much in fishing. But yes, there is. Of course, Oban to the Sound of Jura is a marine protected area. But it's a marine protected area for flap escapes, mobile species. So there are certain areas where you can still trawl. The gentleman behind, sorry.
I used to work for a company called Ferranti, and we supplied the inertial navigation systems
yeah.
for the oil industry.
Yeah.
So that these were used for drilling, so you could actually they actually controlled themselves where they were looking. I just wondered if you used IN systems.
Yes, we do. Yeah, we use an INS, a Carefort from Massachusetts, an American one. Apologies. And that uses a laser guidance system, which is interesting. Laser guidance, sadly, it's the same technology that's used in missiles or rocket technology. So our autonomous underwater vehicle is a restricted item, so we can only use it in NATO countries, a diminishing amount of countries probably at the moment.
Just a bizarre question. On the wreck of the Breda, is it still with the left-handed sandals on it?
Is it what, sorry?
Left-handed sandals. I dived it years ago and it had the left-hand... Just
Left-handed sandals?
No right.
No right-handed sandals? Possibly. I know there's rolls of rupees and things. I've never seen a sandal yet. But there probably is. I'm not going down in the mud, that's for sure. It's horrible. Yes, sorry.
Have you got your own vessel that you can launch the AUV from, or do you wait till you see?
Yes, we've got our own vessel, which is called Sholmara, and she's a 9-metre long vessel. She was built in 1974, and we're currently looking for donors to get us a new vessel. She's quite old, and I know that you'll be very generous on the way out. We're really, really keen to hear from people who would help us with a new vessel for teaching, a new vessel for everything. So thank you very much. Yeah, brilliant. We'll be in touch. Thank you.
Whew. That was a good, what year was that? First or second year? Third year level? The lecture?
Oh, it was probably a first year. This is definitely where I'm more comfortable.
Yeah. John, thanks very much.
I'm slightly prejudiced with marine background, but never mind. We had a talk in October from Alan McCurdy about the geology and landscape of Scotland. And so it's really interesting to see the subtidal bit, which is the much larger part of Britain. So it's it always amazes me just how we don't have national programmes for monitoring all sorts of things.
Yeah.
And you think the seabed, given all that's going on geopolitically just now, you'd think it would be an amazing thing to do. But there you go. We're at least glad that somebody can do it, and we've got the skills and the knowledge and the equipment to do it. So you never know, you might be getting more contracts. Keep your fingers crossed. So, yeah, I think there's amazing work going on at SAMS. Given it's a charity, it's quite amazing that they actually keep going. So thank you very much for coming down from Oban. And yeah, we'll maybe get some of your colleagues back sometime.
Absolutely.
Because there's so much interesting work going on. So if you put your hands together again, please, and thank John for coming down.